Yeah, well, thanks. I figured I would take a few minutes to just set the context of why Rev cares about speech recognition, and give a little bit of history overview of Rev, and then I'll let Jenny explain the cool stuff and the technical, aspects of our work. So at Rev, our founding mission has always been to create work-at-home jobs for people powered by AI. And so what Rev is a double-sided marketplace that enables people to work from anywhere in the world. And the work they do is they transcribe, they caption, or they subtitle media. I sometimes call it Uber for transcription, right? And so imagine before Rev, if you wanted anything to be transcribed, you'd have to go to like a website like Upwork or Fiverr or maybe even Craigslist, find a transcriber, make sure they're good at what they do, negotiate a price and so on. And, you send your audio and you kind of hope that they do a good job. There weren't many very good websites catering the single user for transcription. Today, when, now that we've built Rev, you can, as a single user, just come to Rev, drop a file, in a GUI, put your credit card, and a few minutes later, you get a transcript. And so we really set out to turn this cumbersome, process into some more of a magical experience, and so everything is hidden for you. You just give your audio, you get a transcript back. And today Rev has over 170,000 customers. And more importantly, we create work at home jobs for over 60,000 people. We call them Revers. And the result of having this amazing marketplace is that we transcribe over 15,000 hours of media a week, which, if you think about it, is like producing training data for ASR, right? So if you're vaguely familiar with ASR, one of the most classic data set is called LibriSpeech, and it's about 1,000 hours. And most, people in the research community uses, data sets that are around 1,000, 2,000. There are a few bigger data sets nowadays that are coming out, but 15,000 hours of data every week is like a massive amount. So, quickly, why do we care about ASR at Rev? It should be a bit obvious, but, as a marketplace that does caption, subtitles, and transcription, powering our Revers with AI means using speech recognition, right? So our biggest customer is our internal customer. We run every file that we get at Rev through a speech recognition engine to produce a first draft so that the transcribers can go ahead and kind of fix it and, work with that draft. But we also offer our API externally on Rev.AI as a way for people to build their own voice applications, like if you know a company called Loom or Descript, both great companies powered by Rev.AI. And as now Jenny is showing this slide, we've accumulated a lot of data over the years. 200 minutes is like 200 million minutes is over 3 million hours of transcribed data. So we have this massive amount of data. And the question really becomes, how do we use that data to create, world-class ASR models? And I'm happy to hand it over to Jenny to show you some technical aspects of Rev. I hope you enjoy it.
Thanks, Miguel. Very excited to be here today. I actually did my PhD at MIT. I graduated in 2020. And I've been at Rev since then. And really my main project since coming to Rev has been developing our new end-to-end deep learning ASR model that we're very excited to have in beta release right now. So today, what I'm going to be walking through, first, I'm just going to talk a little bit about the performance of this model and sort of why we're so excited about it. But then I'll go back to the beginning and sort of talk about the development of this kind of model, the modeling choices that go into end-to-end ASR, and especially the big learning experience it's been for me to go from an academic setting at MIT, where the models I trained were just for me to use and test and ultimately, report their performance, versus developing a model that customers are going to actually use and sort of all the extra things that go into that. So this model that we're releasing now we're calling it version 2 of ASR at Rev. So version 1 was what's called a hybrid architecture. It had some deep neural network components in it, but also a lot of other things going on based on, probably 30, 40 years of research into really specific aspects of the speech recognition problem. And deep learning has really come along and blown a lot of that out of the water. It's pretty incredible. So we're really excited to have this model now and be able to share it. So as I said, the first thing I wanted to talk about is just sort of the performance of this new model that we're releasing. These are results on a data set that we've actually released. This is just test data, so it's basically a benchmark that we can use to compare ASR systems against each other. And this data all comes from earnings calls from public companies, and we think it's more representative than what's out there sort of in the academic community. It's more representative of the types of data that we actually see on Rev and what we're interested in transcribing for our customers. The y-axis of this chart is word error rate, and that's really the standard metric for ASR, the way we measure our performance. So for this case, we took all of these earnings calls and we actually submitted them to Rev.com to get gold standard transcripts from human transcribers. And we use those as our references, and then we compare the ASR output to those. And word error rate as a metric, you can probably guess, since it has error in the name, is measuring how many errors that we make. And so lower is better in this case. We want to make as few errors as possible in our ASR system. So what I'm showing here is a comparison of several of our competitors that have open APIs that you can run audio through and get transcripts back from. And then our hybrid model from Rev, which was version 1 of our ASR, and then end-to-end our new V2 ASR system. So the first thing I wanted to highlight on the left-hand side is the overall word error rates of our models. So because of the amazing data resources that we have at Rev, and I'll talk a little bit more about how we use that data in a minute, but because of the really incredible resources that we have, we were already getting really great performance out of the hybrid architecture that we had previously. But now with end-to-end, we're able to get additional significant improvements on top of the really nice performance that we already had. The other thing I wanted to highlight on this chart, so the rest, other than the sort of overall category, the rest of the categories shown on this chart are different types of entities that occur in our transcripts. So we label those entities and then calculate word error rate just on those words to get a sense of how well we're performing on different types of words. I wanted to highlight in particular the org entity, which stands for organization. So this is essentially company names, and the person entity. So these are both things that come up frequently in earnings calls, and I would say arguably are the most important words in the transcript. Getting these words right is really imperative to make it so that someone who's reading the transcript can get the same information out of the transcript as someone who's listening to the audio. So what you can see is that we are doing a really good job relative to our competitors on these words, which is exciting for us. But you can also see that these types of words are definitely some of the hardest ones to get right. And our error rate is still quite high overall. So I just wanted to illustrate, speech recognition, it's definitely, even in English, it's definitely not a solved problem. And we certainly have plenty of work we can keep doing to try to improve on this. The next set of results that I wanted to show are on a test benchmark set that we did not create, but that's an open source data set designed to help research groups understand the bias in different ASR systems. So here we have our end-to-end engine compared against just a couple of our competitors, and the data has been broken out into different nationalities according to the speakers. And so this is something that's really important to us and something that we make sure to track and that we're constantly trying to improve on. So here we can see we're definitely doing a good job on what I would call the maybe most common accents that you might expect to see, in a US-based company. We certainly get a lot of data from the US, but also, Canada, England, Australia are large English-speaking companies, and we do well. Sorry, not companies, countries, and we do well on data from those nationalities. One thing that's really interesting about end-to-end models is that it can be hard to really track down and understand why a model does well on certain particular things and not well on other things. So one thing that I think is interesting in this data is that it turns out we do quite well on Scottish accents and very poorly on Irish accents. So bias is definitely something that we are constantly working on and trying to improve on, and that our research team is very interested in. So I just wanted to highlight again, we're very excited about the performance of our models, but there's always work to do in terms of trying to improve them. So now that I've talked a little bit about model performance, I want to go back and start from the beginning and talk about the development of an end-to-end model for speech recognition. And a little bit about the process we went through in terms of making modeling choices and trying to get the best results that we could. So I hope you've learned over the course of this week in this class that data is really the foundation of any machine learning model. Without data, there's not a huge amount you can do. As Miguel talked about earlier, luckily for Rev, data is something we have in abundance. We're very lucky on that front. And for speech recognition in particular, when you think about it in comparison to other, say, language tasks, something like language modeling or machine translation, there's the aspect of learning to model how text is generated, which is a difficult problem in and of itself. And speech recognition, our models have to be able to do that. But given that we have audio input, the models also have sort of an extra level of difficulty in terms of having to learn what information in the audio signal is important and what information is essentially irrelevant to our speech recognition task. One thing that's very different about developing models at Rev, or I think really anywhere in industry versus in the academic setting, is that academic literature and the benchmarks that people use, Miguel actually already mentioned LibreSpeech, those models tend to cover really relatively small domains where all of the audio seen both at training and test time was recorded in relatively narrow conditions. For us, our goal is really to produce a model that can handle anything our customers want to throw at it. So any audio that gets submitted to Rev.com, we want to be able to do a good job transcribing it. And that's a much larger and more difficult problem than you tend to see in academia. So Miguel showed the slide earlier with sort of the tip of the iceberg of the data that we're actually using to train our models currently versus the data that we have access to. The most important data selection we do before we train our models is that we've decided as a team, at least for the moment, to only use what we call verbatim transcripts for model training. The verbatim product on Rev.com asks transcriptionists to transcribe literally everything that's said in an utterance. So this includes things like filler words, disfluencies, any errors, things like that. Everything that gets said gets transcribed. Most of the data that comes through Rev.com gets what's called non-verbatim transcription, where transcriptionists have the option and the ability to sort of make small corrections with the goal of making the transcript as readable as possible. But for us, for ASR training, it's very important that we get everything that's said. Several of our customers, Miguel mentioned both Loom and Descript, actually have as part of their product that they flag disfluencies and filler words. And in some cases, like in Descript, I believe you can automatically remove those from the audio based on our ASR output that says where they are in the audio signal. So it's very important to us that we get those correct. The next piece of preparing to train a speech recognition model is to actually break the input down into segments that we can train on. Our audio data that we get is often long files, so it could be 20 minutes, could be several hours. So long files of audio and transcripts, and it's not realistic to, feed one whole 20-minute audio and the transcript for it into a deep learning model and try to, back propagate through that entire transcript. Typically, what you see again in academia is data sets broken up into single sentences, both at training time and test time. For us at test time, we don't know anything about segmentation, and we have to essentially segment the audio arbitrarily. We do some what's called voice activity detection to try to segment the audio around pauses, but people don't always pause where you think they will. And so we found that actually we can get the best results from our models if at training time, we split up our training data into essentially arbitrary segments of different lengths, and also including multi-speaker segments. So having some segments that go from one speaker into another speaker, that actually gets us the best results. In terms of speech input to these models, speech, or I should say audio, is one-dimensional signal that's high frequency. So typically we see 16 kilohertz audio, which means 16,000 samples per second, where each sample is just one number. It is possible to feed that to a neural network and essentially learn features from it, but we find that everything is sort of simpler and easier to handle if we first do some pretty simple signal processing to turn our audio into a spectrogram like you see in the bottom image. So what we use as input is a series of vectors. We have one vector typically every 10 milliseconds, and the vector has the energy in the different frequency bins in our signal. And it is possible also to think of that signal as more of an image like you see here. And I'll talk a little bit about how some of the sort of low-level processing we do in the neural network has some commonalities with what you might have seen in networks for image recognition as well. The next piece of the model, I think you guys might have seen this before, sort of in the language modeling context, so I'll go over it quickly. But a really important piece of the model is deciding how we're going to break up the text data in order to have the model generate text output. So one option is to produce output word by word. Another option would be to break everything up into characters and produce characters one at a time. If you go the words option, you tend to have sparsity problem in that your model can only generate words that it saw during training, and realistically probably can only generate words it saw multiple times during training. So a lot of rare words will just sort of be inaccessible to your model if you go that way. With characters, we don't have a sparsity problem. There's a very small set of characters, and the model will definitely learn to generate all of them. But now you have often very long output sequences, and it becomes much harder for the model to learn sort of longer range dependencies between words. So like in the language model case, often it's important when you're generating a word to look back, maybe several words, maybe back to the beginning of a sentence. And in the character case, that can be very far away in terms of the length of the sequence. So what the field seems to have kind of settled on is the use of what are called subword units or word piece units. So here we break words up. Sometimes some of our units are whole words, but the words can also be broken up into units that can be single characters or longer than single characters. In speech recognition, we generally use the same techniques for this that are used in language modeling or like machine translation. So either what's called byte pair encoding or a unigram model for this. They're both a bit heuristic, I would say, but they tend to work really well in practice. And this is sort of what the field has settled on.
Jenny, before we move, Ben had a question about some of the design, the decision process around using Melscale, Mel frequency scale versus other approaches?
Sure, yeah. Happy to jump into that a little bit. This is definitely something that is sort of left over from older speech recognition research. The Melscale, the way these filter banks are set up, is designed to sort of mimic actually the way the human ear processes audio. So humans actually can do a much better job of distinguishing between lower frequencies than higher frequencies. And so this is intended to reflect that. As I said, there are some neural network models that can take a raw audio signal and essentially learn these filters as part of end-to-end model training. My understanding is that for the most part, they tend to learn filters that look kind of like these ones. And I haven't seen results where that really ends up adding any extra accuracy from just doing the signal processing upfront. So for us, we just find it much simpler to do it in signal processing rather than include it in the network.
Nice.
Is that cool?
Thanks. Actually, just for reference, the question was around Melscale versus Bark scale, and I've actually never heard of anybody using Bark scale in speech rec, so I don't know exactly why that would be, but I'll look it up after this talk.
Yeah, go for it. I'm also not sure. I've heard of it, but I think Melscale is definitely standard for speech recognition. It seems to be what everyone uses. All right, cool. So moving on to the actual deep learning modeling choices, I wanted to start with the encoder decoder model with attention, again, because I believe or hope that you guys might have already seen this a little bit in a previous lecture. And the reason why you might have seen it before is because this is a very standard generic model that really could be applied to almost any sequence-to-sequence problem, and speech recognition is no exception. This works very well for speech recognition. So this is, at a really high level, what our model looks like. And just really the key thing to remember about these models is the autoregressive decoder. So these models produce output 1 unit at a time, and each output as it's produced is fed back into the model to bias what the next output will be. So another way to think about it, if you've been exposed to neural language models, but not this kind of model before, is that essentially the decoder is a neural language model, but it's also conditioned on embeddings of the input audio. So for speech recognition, there are just a few basic choices to make about these architectures. As I said earlier, you can sort of think about our speech features as an image. And we actually do a first embedding layer in our encoder that looks a lot like sort of the low level layers of a VGG network for image recognition. If anyone has seen that, but basically we just do some convolutional layers to pull out low level features from our speech features. Here in the embedding, we find that it's also useful to just do some downsampling. As I mentioned earlier, typically we use 10 millisecond frames as our speech features. So that's 100 frames per second. So the output sequence is much longer, the input sequence is much longer than the output sequence. So it just makes things simpler to sort of downsample everything up front. So we typically downsample by a factor of 4. And then if you're using a transformer layer, as I'll talk about in the next part, this is where we also add relative positional encodings. And this helps the transformers. It gives it more information about where in the sequence each input feature originally came from. And then, as I said, there's a choice about what kind of actual layer to use. Recurrent neural networks were very standard until really very recently. It's been a very quick change towards transformers, but transformers are definitely very popular and they're very effective in speech as they are in other arenas like language modeling. And this nice feature about transformers that they're actually quite efficient at training time is definitely a plus. If you're training really big models on a lot of data, which is what we're doing, having more efficient training is definitely nice. We actually use something that's called a conformer. I think I've only seen it in the speech recognition context, but I wouldn't be surprised if this is something people are using for other types of problems. It's pretty simple. It just has, this extra convolutional layer sort of stuck after the self-attention layer of the transformer. And these have been shown to be sort of a bit more efficient in terms of being able to get slightly better performance out of the same number of parameters, or similar performance out of fewer parameters compared to a pure transformer model. So attention-based ASR models work really well. Definitely, it's been a little while now. It feels like a long time in sort of the deep learning world, but really not that long since they sort of officially surpassed the older hybrid architecture in terms of performance. And that was with recurrent neural network models. So with transformer models now, we see even better performance out of these models, like some really impressive numbers that I think people thought we might never hit in terms of accuracy. But there's a big problem here, and one that I was actually not really aware of. I wrote my entire PhD thesis on attention-based ASR models. But now that I'm at Rev, I realized that these models are just not practical for commercial applications. So it's very hard to have, a big enough model that gets good performance that's also fast enough to use for inference. For us, we offer two different products with our ASR models. We have streaming, which means like live captioning. So it's very important that the transcription process be fast enough to keep up with audio. But even for offline speech recognition, where speed is slightly less important, there's still trade-offs to be made related to compute costs and whether it really makes sense to offer a product at a price that customers are willing to pay. So ultimately, these models are great, but we actually can't use them at Rev in production. So what do we do instead? It turns out that there's this older algorithm called Connectionist-Temporal Classification, or CTC, that's actually very well suited to ASR and forms the backbone, I think, of most of the industry speech recognition systems that you'll see, and certainly is the backbone of ours. So CTC is not a generic sequence-to-sequence algorithm. It only works for certain types of problems. In particular, it's really best when the alignment between your input and output is monotonic. So for speech recognition, we definitely meet this criteria, but something like translation, where depending on your languages, the alignments could be kind of all over the place, would not work well with CTC. Another sort of criteria is that the output sequence should be the same length or shorter than the input sequence. Again, this is perfect for ASR. Our input sequences are very long relative to our output sequences. But again, something like translation, you don't know necessarily whether the input or output sequence will be longer for any given example. And CTC is, it's not a model architecture exactly. It's actually sort of a loss function and a decoding algorithm that sits on top of a deep learning model. The main properties of the models that we use for CTC is that the first one is that they are not autoregressive. So unlike the model we saw previously, where our outputs are produced one at a time, and that really contributed to sort of the slowness in the inference process. Here, we don't have any of that feedback, and the outputs are generated sort of all at once out of the model. And some of the probability calculations I'm going to talk about on the next slide are dependent on the assumption that the outputs are conditionally independent given the inputs. The other thing you need from a model to be used for CTC is a softmax output layer. So this is the same thing you'd see with an encoder decoder model. With attention, you have the softmax layer, and that gives you each output is a probability distribution over your output vocabulary. So like your list of characters or subword units. For CTC, we add one extra symbol to our output vocabulary, which is a blank symbol. And I'll talk on the next slide about how we're going to use that. So with the encoder decoder model, which again, I'm hoping you saw a little bit in the past, but essentially you can just calculate the probability of your output sequence by summing up the log probabilities that you have in each of your softmax outputs for each time step. So here we can do the same thing, assuming that we have an output sequence that's the same length as our model outputs. Our issue is that typically what we want to calculate is the probability of a label sequence that is shorter, in the ASR case, much shorter than the output sequence. So the way we do this is we say the probability of the sequence Z, this shorter sequence, is simply the sum of the probability of all of the longer sequences that reduce to Z. And what I mean by reduce, so Y reduces to Z if Y and Z are the same once you remove all of the blanks and repeats from Y. So I have a couple examples down here. If our desired output sequence, say we're using characters, is 3 characters long, it's CAT, but our model outputs are 4 characters long, then here are a couple examples of 4 character output sequences that reduce to the 3 character output sequence CAT. So for this simple example, you could actually just write out all of the different Ys that reduce to this labeling, and you could calculate their probabilities individually and just add them up. But as these sequences get large, that's very inefficient. There's a lot of redundancy in the different sequences, and just the length of the list of probabilities that you need to add up gets very long. So what's nice about CTC is it comes with a really elegant dynamic programming algorithm that lets us very efficiently calculate this probability of Z given X, and also can be easily modified to be used in decoding with an algorithm that's called CTC prefix beam search. I'm not going to get into the details on this, but I actually think this original paper is really nice, and I would definitely recommend anyone who's interested go back and read it. So CTC, in terms of performance, it's definitely not as good as our encoder decoder models, but it can be better than the hybrid models, and at least in the right conditions. So we're moving in the right direction. In particular, recent advances in terms of transformer or conformer models and large data make CTC work pretty well. And what's really nice is that the decoding or inference is very fast. So it's even faster than the hybrid model, and it's much faster than the attention-based model. So now we've found something that we actually could put into production. I think I'm going to stop for a second, just to ask, what are we thinking about timing? I know we started a tiny bit late. Just wanted to check in.
Yeah, that's. I don't know how much time you have sort of in your deck, but we can take another 5 to 10 minutes or so. That's okay.
Okay, great. I'll try to move a little bit quickly, but I think that's very doable. Thanks.
Awesome.
So yeah, I think CTC is just a really good reminder that even though these deep learning models are incredibly powerful and the results can be really amazing, it's not always the best idea to just choose the most powerful model possible and throw as much data at it as possible. That we can still get real benefit from our computer science fundamentals and thinking a little bit more deeply about the problem. I think that's always a good lesson in this context. So despite the CTC model being, reasonable to use, like I said, it can be better than the hybrid models, and it is faster. We still want to see if we can get closer in terms of accuracy to the performance of the encoder decoder models, while still keeping the efficiency reasonable for inference that we could actually put it into production. So there are a bunch of different ways we can do this. The first one is to add an externally trained language model. So CTC, the way the beam search works, it's actually very easy to take scores from a language model and add them in. Technically, this is no longer an end-to-end model because now we have a language model that's trained separately, but in practice, it does work well. So we can use any kind of language model, whether it's a neural language model or an n-gram model, sort of an older statistical model. And that model can be trained either to predict words or subwords. If it's subword level, it should be the same vocabulary as as the ASR model itself. And these combine well. There is some cost, obviously, to getting the probabilities out of the language model. So there's some trade-off here between accuracy and speed or compute cost. If you throw, a humongous transformer language model in there, it definitely is going to slow things down. So it's still there's still some work there to understand, what the trade-offs are and what makes the most sense. If we want to stick with a pure end-to-end model where all of the parameters are trained together, it's actually possible to basically add a language model to CTC as part of a deep neural network model. And this is called transducer. I think I most commonly see it called RNNT, even if there are no RNNs in it anymore. It was RNNT when it was originally introduced, but definitely, as I said, transformers have kind of taken over. But anyway, this model here, the prediction network, the sort of green box in the diagram on the bottom left, is essentially a language model. So it takes previous outputs from the model and updates this hidden embedding based on those previous outputs. But this can be trained with the CTC loss and can use the same CTC decoding algorithm. And again, assuming that the prediction network and joint network are relatively small and not too costly, this can definitely still fit into sort of the compute budget for a production system. The last thing I want to talk about is what we have actually decided to do at Rev, and that is a joint CTC and attention model. So this is the encoder decoder model with attention that we saw previously. So we can take the encoder, just add a softmax layer and turn the encoder into a CTC model. And we can train all of this jointly by just adding the CTC loss and the attention-based loss together. And what this gives us at the end is essentially two complete models that just share encoder parameters. This was originally developed as a way to actually improve the accuracy of the encoder decoder model with attention. So there's a way to do the attention decoding while also incorporating scores from the CTC model. And that actually gives, I think that's the best performing ASR architecture overall that I've seen. But it's similarly slow to the encoder decoder model with attention. So what we do instead is we use a two-pass decoding framework. So first we pass the audio through the encoder and we get our CTC, we use our CTC decoding to get an n-best list of hypotheses. And then we can use the attention decoder to do what's called rescoring. And so here we're able to feed each hypothesis that came out of CTC decoding into the attention decoder and get the probability of that hypothesis according to the attention decoder. And what's nice about this is that we can actually do some of the parallelization that we saw during training in transformer models, and we can do this at inference time as well. So here we're able to get actually word error rates very close to what we achieved with attention decoding, but it's much faster than attention decoding is. So I have a couple of slides about like research projects that we're working on, but I think I will pause and we can take questions. Here. Yeah.
Awesome. Thank you so much, Jenny and Miguel, for such an illuminating talk. I think really touched on a lot of concepts and also connected them back to some of the topics we introduced in the lectures, which we really appreciate. Maybe as people are thinking of questions, I can start with one. The results you showed with respect to bias in the data sets and potential effects on model performance were very intriguing to me. I'm curious if you can speak a little bit more to strategies that you're exploring for trying to handle and mitigate these biases in your ASR pipeline.
Yeah, absolutely. So one thing that we already do to a certain extent, but we're looking into doing more of, is actually making more use of our Rev human transcribers to have them help us label data with accents. We have some labeling, but the more data we can collect, the better. The ultimate goal of that is really to do a better job of balancing the training data. We think that's probably the sort of easiest approach in terms of getting the models to do a better or less biased job across different types of data. We are also, we have looked, at least in the past, with our hybrid model, and I think it's something we would consider as well for this end-to-end model, is sort of post-processing steps that can potentially account for some of these issues and try to do some error correction after the fact. Yeah, I think those are our two main strategies at the moment.
Yeah, if I can add that, if you remember that iceberg, slide that I showed, I think the answers are hidden in all the data, and a big part of it is like us figuring out a way to mine that data and rebalance things, as Jenny said. And there's a few techniques, I think, to learn, like curriculum learning and things like that maybe we could explore. One of our research papers is around curriculum learning.
Very interesting. Yeah, I'd love to follow up on that topic later on. Thank you.
Sure. Yeah. I see one question in the chat about the first pass that we use in the two-pass model. Yeah, so for right now, actually, we are looking into the transducer models, and it's definitely something we're interested in. Those seem to perform well, but we're currently using CTC with an n-gram language model added after the fact as our first pass. And that is conformer, the encoder that we use for both CTC and the embeddings that get fed to the attention decoder is a conformer model. Thank you. And I just wanted to say quickly, I did put our email addresses here. Definitely feel free to reach out if anyone has other questions or wants to talk about Rev or just ASR in general. I'm always happy to chat with people. Thanks.